is Francois Germinet, and he's going to talk to us about localization for Schrödinger operators with Delone potentials.
Well, thank you very much. Thank you very much for this very kind invitation. It's a pleasure to be here 4 years after this wonderful meeting that we had in 2008. So I will speak about localization for Schrödinger operators with Delone potential. This is actually a joint work slightly in progress with Peter Müller and a former student of mine, Constanza Rojas Molina. And I will also, meanwhile, mention some recent results that we get with Abel Klein. So let me describe the setup. Well, it's a well-known setup. I consider operators in the continuous case, so on L2 of RD, d-dimensional, and this is just one particle, and HD is equal to the Laplacian, so the continuous Laplacian, and a potential VD. So what is VD? VD is an holotype potential, and it reads like this. There is no randomness yet. You have a single side potential U, which is a bump. Okay, so let's think about a positive bump, and you put your bumps at different points of your space. Okay, so you translate your little bumps at a point zeta, and zeta belongs to my set D, and D is just a point set. Okay, so a discrete point, a discrete set of points of RD. So as I said, the single side potential U is non-negative, bounded. It's a measurable function with compact support, and it is uniformly bounded away from zero in some neighborhood. So U is just a function like this. And at each point of ZD, you have this potential. At each point of D, you have this potential. Okay, so if it is well known, of course, that if D is a periodic set, then you get absolutely continuous spectrum. Okay, but now, what if D has a more complex structures, like Delone sets? So you have sets which are not really regular. There is no symmetries. No translation invariance, etc. And you still put your bumps at these points and with these more complex structures. And what do you get? What type of spectrum do you get? The motivation goes back to quasi-crystals and in particular to Shechtman, Blech, Gracias, and Kahn. And well, I'm sure you have seen pictures like this, but this is just to refresh your minds and give some pictures on what happens, what's happening. So when D is periodic, then you get a crystal, and if, for instance, you look at diffraction patterns, then in this case you see something very regular with many symmetries. And if D is a quasi-crystals, so something slightly more complex like this, then you get a different patterns where in this case translation invariance is broken, but you still in this case get some symmetries. But you also have situations where there is no symmetries at all. I will be interested in a way of let's say describing this more complex set of points. And the name for such sets is Delone set. And there are two parameters coming into the game, little r and capital R. Little r means that points of D are uniformly discrete, that D is uniformly discrete, and capital R means that D is relatively dense. So you don't have too many points, and they cannot come too close one to another. But on the other hand, you have sufficiently many points in the space. Here is a picture. On the right, you recognize the lattice, and on the left, you have on the very left, you have well, a typical Delone set. You see that all between 2 points, I always have at least a distance little r, but it can be bigger than that. And in any ball of radius capital R, I do find a point of my set D. Okay, and one particular example of Delone sets is famous Penrose tiling. Okay? So let me repeat: if D is a Delone set, then I construct this operator. This is exactly the same that I described on the first slide. Okay. So the spectrum, there is a very nice result going back to the 90s, and there has been some developments in the year 2000s, saying that the spectrum of this operator is generically purely singular continuous. Okay, within the sets of all Delone sets. So there is a way to put topology on the set of Delone sets, and with respect to this topology, these people showed that the spectrum of HD is purely singular continuous. And there is one result, maybe if you are interested in this, you should look at the paper of Daniel Lenz and Peter Stallman, where I think this is done in most generality. Okay, so well, we have the answer.
That's
Yeah.
not a measure theoretic statement, right?
No, it's not.
It's kind of a homological.
Exactly, it's not measure theoretic. Yeah. So we could say, well, we have the answer. The spectrum is generally.
If spectrum is singular continuous, what you can say about the eigenfunctions? So they are extended, but not ergodic, or what?
Yeah,
what can we say about it? Yeah.
Well, first they do not describe the eigenfunction, but of course they are not localized. They are not sufficiently well localized to be L2, but most likely they are not flat. They are not. You do not have plane waves or things like this. Okay, and my guess would be that depending on the regularity of the Delone set, you will have different type of behavior of the eigenfunctions, because between a very between a very random situation like this and something with some symmetries like this, you can get different behaviors. Okay, I will mention that later on. Well, we have the answer. The spectrum is generically purely singular continuous. But let me still ask the question. Can we get, for Schrödinger operators of this form, can we get still some localization at the very bottom of the spectrum? Namely, for some kappa strictly positive, look at the bottom of the spectrum, sigma inf and sigma inf plus kappa, and show that well, the spectrum is not empty, and that there is some localization with L2 exponentially, well, L2 eigenfunctions with an exponential fall-off. And note that there is no randomness here yet. The answer is actually yes. We can find Delone sets with parameter little r and capital R, for which you don't get purely singular continuous spectrum, but you do get some Anderson localization of the bottom of the spectrum. Well, then you may ask how many, and for these two questions, how many and how regular they are, then this is still work in progress. So I will not say a lot about that, but from a topological point of view, my guess is that we actually get a dense G delta, and actually a union of such a dense G delta. Yeah. And so there are actually many.
So what does it mean on the possibility of finding a localized state?
Well, this means that for a large family of such operators, you will get localized states. Okay, I will come to it.
But the spectrum is singular continuous.
It's not. The spectrum is purely singular continuous for a family of such operators.
Family, but there are other families that...
Yeah. Okay, what I have in mind, if you want a comparison, is the famous almost mature operator. For this operator, if you take a Liouvillean frequency, then you get singular continuous spectrum. While if you get Diophantine frequencies, then you get Anderson localization. So if you want to compare to this situation, my guess is that, or my interpretation is that this result corresponds to the Liouvillean part. So this corresponds to Delone sets which are rather regular. Okay, but now if you look at more irregular Delone sets, then it's just like with Diophantine conditions for the almost mature operator. You should get some localization, and this is what I am interested in here. Okay, so I will construct some Delone sets, and what I can say is that they are rather irregular. And for instance, they do not exhibit what is called uniform pattern frequency. Okay, because actually there is an infinite number of patterns that are repeated an infinite number of times. Okay, so to prove this, I will make a little detour.
So what are you going to prove?
I will prove that for a family of Delone sets that I will describe later. Okay, it will come later.
Are you not making them random, as you said? Are you making those random?
Well, I will make a detour, but at the end, the result will be deterministic. Okay?
Okay.
So I will use randomness to construct my families, but from the very, from the very beginning, what I'm interested in is deterministic operators. So there is no random coupling constant in front of my bumps. Okay. Okay, so a detour, and I don't have much time, so I will go quick. A detour to Anderson Hamiltonians, which is closely related to the topic of this conference. So the background is the following. I have a Laplacian and a periodic potential and an Anderson type potential, okay, still in the continuous. And this is some joint work with Abel Klein, okay, what I will describe now about this continuous Anderson Hamiltonian. So it's like before, V omega corresponds to this alloy type Randolph potential, and U zeta is still my single side potential translated at point zeta. Zeta now belongs to a good lattice, ZD. And the novelty compared to before is that now I have a random coupling constant in front of my single side potential. Okay, that's the usual one. And my omega zeta consists in a family of independent and identically distributed random variables with some common probability distribution mu. And the only thing I consider, I ask is that mu is not degenerate. Okay, so it's not just a single point. It is actually it is a probability.
The periodic potential is ZD periodic, yes?
Yes, it is ZD periodic. But actually, it will not matter for what will follow. For the result, yeah, it will not matter. I mean, what I mean is that we can relax this. What you just said. Okay, so the only thing I assume is that mu is not supported by on a single point. So there is actually randomness. So at least 2 points, Bernoulli or whatever you want. So the theorem we prove with Abel Klein is the following one. take these Anderson Hamiltonians, and we show that it exhibits a strong form of localization of the bottom of the spectrum, and without any additional condition on the single site potential distribution. Okay, this strong form of localization holds at the bottom of the spectrum. Okay, and it includes Anderson localization. That means pure point spectrum with exponentially decaying eigenfunctions, and dynamical localizations, namely the non-spreading of wave packets under the time evolution. And moreover, we can say something about the integrated density of states. We can actually show that it is a log order continuous at the bottom of the spectrum, namely where we have localization. And this is something also new at this level of generality. So a few comments. This holds in arbitrary dimension. In dimension 1, I think this was known much before. If the single site potential, the single site probability distribution mu has a bounded density, then there has been a lot of work on these models, and one can even get stronger results than what I will present. If mu has a Bernoulli distribution, so mu is supported on 2 points with and you have weight 1/2 and on one point and 1/2 on the other point, then the proof goes back to Bourgain and Koenig in 2005, the proof of Anderson localization. And in some sense, the theorem that I showed you before on the previous slide is a full version of Bourgain-Koenig plus a generalization of it. Yeah. Okay. Okay, and spectral localization for this model has been shown by Eisenman, Klein, Warzel, and myself in 2009. So, but just pure point spectrum. Okay, but now not the full picture of localization, but just pure point spectrum. Okay, so in some sense, this is the I mean, what I present you is the full version of the result. And as I said, the proof is based on multiscale analysis, and we incorporate ideas of Bourgain and Koenig. More comments. If you now consider not points on a lattice, but single site potentials distributed on points that are thrown at random in the space, according to a Poisson process, then we already proved with Hislop and Klein and myself Anderson localization in 2007. Okay, and let me mention some related open problems. Surprisingly, we can treat the continuous case, but we cannot treat the discrete case. So discrete Bernoulli-Anderson model case, we cannot do it. Because actually there is no there is no unique continuation principle in the discrete case, and we cannot treat Landau Hamiltonians plus random potentials. Okay, there is a problem with some exponent in the quantitative unique continuation principle that we use, and it also works if the single site potential U is either positive or negative, but if it changes sign, then we cannot do it. So still there is some work to do. Okay. Some notations. I will go very quick. Lambda L of X is a box, okay, of size L and of side length L and of center with center X. Chi of X will be the characteristic function of a unit box, okay, and I will use P for spectral projections. Here's the result. The log order continuity of the integrated density of states. The result looks like this. At the bottom of the spectrum, so between the infimum and some E0 that is strictly bigger than the infimum. As soon as E2 minus E1 is sufficiently small, then the difference between the two, I mean the integrated density of states between E2 and E1 is smaller than this. Okay, so we get log order control.
And how big is
With
kappa?
some kappa. And actually kappa is 38 D. Well, anything slightly better than this. So I mean, it's not great, but so far that's the only thing we can prove. And note that it improves with the dimension. Yeah. And let me remind you that in the regular case, so when the probability distribution is regular, then what you get is exactly the modulus of continuity of the measure, like this. Okay. So you get something better unless mu is more singular than log order, of course. Okay. So now some details of localization. I will not show everything to you, but still a little bit. We get Anderson localization in the sense, you see, that if I look at my eigenfunctions around the point x, then it decays exponentially like this, okay? And there is some control of the constant that is in front, okay? So you get this exponential decay. The multiplicity is finite, but we cannot prove that the multiplicity is uniformly finite. And of course, we can not even prove that the multiplicity is simple, although, I mean, people expect the multiplicity to be simple, but still multiplicity is finite. And okay, if you look at the 2-point functions, so if phi and psi are eigenfunctions associated to the same eigenvalue, then their 2 points correlation functions decay sub-exponentially. We cannot do better with some beta which is much smaller than this 1/2. So this constant is pretty bad, but it is actually enough to prove dynamical localization from this. And why is it enough to prove dynamical localization from this? It's because here we have a constant that does not depend on the energy. So all the energy dependence is located here in these two terms. And this is summable. If now you sum up your wave packet, if you divide your wave packets in eigenfunctions, then using this you can sum up all these and you get dynamical localization. Okay, if you want now to describe the exponential fall-off of the eigenfunctions away from localization center, then you still get the same thing. Namely this sub-exponential, quite bad sub-exponential decay, with a term depending on the center of localization, with 1/2 which is bigger than this beta. So in particular, this means that if you want to look at the eigenfunctions very locally around the center, then you get something which is pretty bad. And this is not enough. This is a Soulé-like control, and unlike the original Soulé condition developed by Del Rio, Zhytomierskaya, Last, and Simon, this is not enough to prove dynamical localization, but the previous one was enough. Okay. So you have almost sure dynamical localization, namely if you take bounded Borelian function f with some support in the region of localization, you look at the trace of the kernel between x and y, then this decays sub-exponentially. Okay. So you have many features of localization. I will now skip this, and I will come back to my problem. So I finished my detour. Okay, so you have this in the situation of Anderson models with singular probabilities. You do get localization with all the properties that I described, and I come back to my problem. Let me consider a Delone set D1, okay, with parameters little r and capital R. Then I say that you can choose another one, D2, another Delone set, still with parameters little r and capital R, such that when you look at the superposition of these two, you still get R over 2 capital R Delone set. Okay, you can play with these sets, of course. So you just have to put the D2 inside the holes left by D1. Okay, and I would like to consider the following Bernoulli-Delone Schrödinger operator. Laplacian. I have my background potential with single site potentials located at point D1. Okay, so this corresponds to my V0, to my background operator V0 that I introduced before, but this is not periodic anymore. Okay, this is rather irregular. And I add a second potential. This one is random. Omega zeta is Bernoulli, so it is 0 or 1. So for some omega, there is no, this is 0, and for some omega, you just get u zeta. You can.
The only place where you have your randomness?
Yeah, yeah, exactly. So you can consider this random point set, which corresponds to the point zeta of D2, where omega zeta is 1. Okay. So in this case, H omega reads this way, minus Laplacian plus the potential constructed on the points where I have a point of D1 and a point of D2 omega. Okay, and what is important here to notice is that the union D1 union D2 omega is always a Delone set. Okay, even if omega is so that all omegas zeta are 0, then I still have D1 and I still have a Delone set. Okay, so what matters is that whatever is the realization omega, I still have here a Delone set. So what I want to do, and well, what I do is apply the multiscale analysis that I of Bourgain-Koenig, and the point is that this method is not sensitive at all to the geometry of the impurities, and so we can use the Bourgain-Koenig procedure and what we did with Abel Klein to treat this case. The fact that the background potential is not periodic has no impact at all on the multiscale analysis procedure, but the problem is that, I mean, you have a nice machinery that works, but you have to initiate this machinery. You have to start it. And this is here that you can get into troubles. So to start this very nice machinery that will give you localization, somehow you have to prove something like this. You have to control resonances. So this is the Wegener part of my condition, and you have to show that at some scale you have some exponential decay of the resultant. And starting from this, and if you have this with a sufficiently good probability, then you are in business. Sometimes people use Lipschitz tails. Well, it is okay if D1 and D2 are periodic, but in this case, in particular with this D1 that is not periodic at all, then it is not so easy, and I think that it is not done. Since I think I'm almost close to the end. How much time do I have? Maybe 5-10 minutes. Yeah. I will skip this one. I will skip this. I will skip all the details. I just mentioned that if D1 is 0, okay. So if you do not have D1, but just this on this Delaunay-Bernoulli here with no background potential, then you can prove localization using the fact that you are at the bottom of the spectrum, so the energy is weak, and since the energy is weak, you can compare this operator to some average operator for which we have for which we know that the bottom of the spectrum is lifted up. Okay, but what makes the thing difficult with this background potential is that we don't know actually where the infimum of the spectrum of minus Laplacian plus VD1 is. So we don't know where the infimum of the spectrum is. Nevertheless, we have to lift this spectrum using the impurities. Okay, we have to lift the spectrum of the background operator with the impurities to make sure that we have some gap, and then use Comte-Thomas and start the multiscale analysis proving this. Okay. So if D1 is 0, then we can do something, but we do not solve the problem because D2 omega is not, in most situations, is not a Delaunay point anymore, because Delaunay set anymore, because you can have large holes inside your set. You can have large holes, you can have large regions where all the omega zeta are 0, and if all the omega zeta are 0 in a very large region, then you lack the denseness property of the Delaunay set. Okay, so this does not solve the problem. The problem is the following one. This is what I told you. We have to prove that that with a good probability on this omega, the infimum of this spectrum is lifted by a constant kappa from the infimum of this spectrum. So the idea is actually to find some trope, yes, and I will draw a picture. The idea is the following one. I divide this my cube of size L in smaller cubes of size K. Okay, and I ask that at least one of the omega zeta in each of these cubes K. Okay. That at least one omega zeta is non-zero. Okay. The omega zeta may be 0 everywhere else, but I ask that at least one is non-zero. Well, this has a good probability, a probability that is good enough to start later on. So now I restrict myself to the configurations where omega is like this. Okay, so and I will call AK the set of omegas where I have this situation. And the rest of the argument is actually deterministic. I consider the family minus Laplacian plus VD1 plus T times my operator, my potential. And I will come back to this one later. And this is what I do. I will follow some ideas of Rojas Molina and Veselic and get some scale-free and use some scale-free quantitative unique continuation principle. Here is how it works. I have the centers of localization. So these are gamma, and let's call these points x gamma. I consider omega that a gamma. I will say that my center gamma is dominant if the average of my function, so my eigenvector associated to the lowest eigenvalue, if the function on this cube is 1/2 bigger than what happens if I average around a much bigger region of size tk. Okay, so I average over boxes which are around this box, and I use periodic boundary conditions. Okay, and I say that that gamma is dominant if I have this thing. The point is that the sum over gamma which are dominant is actually bigger than half the size of my eigenfunction. So now, if I look at psi h psi, then this is certainly bigger than what happens on this potential. And since here I have all the points, I can sum over all the x gamma which corresponds to a dominant gamma. Okay, and now I apply a result of Bourgain-Koenig saying that, well, I will describe this, but saying that if I have a bound from below on this point at the center on this point, then I can say for sure that the size of the eigenfunction at this point is bigger than so if here the distance is not r but L, then psi around x will be bigger than CL minus CL 4/3 psi around gamma. So you lose something, but you can control this. Okay, you can control this. It depends on the distance between these 2 points. Okay, I will finish the argument and maybe I will come back to it. So now the main point is that since I have divided my my cube in smaller cubes of size k, then I have I don't have something that is exponentially small in the size of my original box. It's not capital L, but it is controlled by k. Okay, little l is smaller than k. So I have a constant that is like this, okay, k minus ck 4/3, and this gives me the gap, okay, it gives me a gap, and the spectrum of h plus d1 plus d2 omega starts above the spectrum of the unperturbed operator plus this constant k to the power minus c k third. Okay. Okay, so I just finished with this, and now if I come back, this means that I have found a gap of size of this size, and when you do Comte-Thomas, well, the size of the gap gives you the mass of the exponential decay. The size of the cube is little l, and this has to be much bigger than 1, otherwise you don't have decay. In my case, k is of the order log L to the 1 to the over d. So this means that if d is bigger than 2, then we get localization. And when d is 1, then you can replace, then you don't have this 4/3 term, you just have 1, because you can use Grunwald inequality instead of this quantitative unique continuation principle, and you still get the result. Okay, so I think, so to summary, this means that we can create a gap so that we can start the multiscale analysis, and for these operators, for these Delone sets, we do get Anderson localization. Okay, and I will just finish by saying that it is my pleasure to to celebrate Leonid's birthday, and I wish Leonid a very happy birthday. Thank you.
Running a little over time here, but maybe we have time for one question. I have a very quick one. If you just have a random Delone set, is it and this is obvious that you have the localization? In other words, random. In other words, you just look at all. You fix the little r and the big R, and you take arbitrary configuration. You give them all equal weight.
You mean randomness in the location of the point?
Location.
So, but according to which to
I
which
just give a
process?
uniform. Can I give just a uniform distribution subject to the constraints?
Well, I think one should get something, but I'm not sure. There is another way of getting localization for this type of model is to use I forget the name. The displacement model. Okay, so you have in each box. Okay, you have a point that is uniformly distributed.
Yes.
Yeah. So maybe that's what.
Yeah, that's pretty close.
So there is a result of Frederick Klopp and who else? Nakamura, Stoltz.
Yeah, that should be very close.
Yeah. And in their case, they need all the points to be quite close from one to another. Okay, and here it's slightly different because you can get points which are very far apart.
Okay, well, let's thank our speaker once again.
Thank you.